So we'll start our study in the first chapter with investigation of the different types of categories that real numbers fall. So a real number is any number that can be graphed on the number line. We can see a number line in front of us. We've got 0 in the middle there with the negatives to the left and the positives to the right. And so we talk about real numbers, which implies that there are imaginary numbers, which we will study later on in the year. Those are a real thing, and those are square roots of negative numbers. But again, for now, we're just dealing with real numbers. And so we want to investigate the different categories into which we can divide real numbers. And so we see those categories listed in front of us below here. So the first and simplest category of numbers are called the natural numbers. They're also sometimes referred to as the counting numbers. And we'll represent those with the letter n. And those are the numbers that we just use to count. 1, 2, 3, and so on from there. There's no fractions, there's no decimals, we don't even have 0 because we're literally just the numbers that we use to count objects. And so from there, we only grow in the size of the sets of numbers that we're looking at. So the next category are the whole numbers. Now there's not a whole lot of difference, excuse the pun, between the natural numbers and the whole numbers. Whole numbers will be represented by the capital letter W. And the only difference between these two number sets, the natural and the whole numbers, is the introduction of the number 0. Other than that, we're exactly the same. No decimals, no fractions. We've just increased the set of numbers by 1 by having 0 in there. Now we also want to use a Venn diagram to show how these number sets relate to one another. So for example, the natural numbers, if we have a circle that represents the natural numbers, so 1, 2, 3, 4, 5, going up from there. If we look at the whole numbers, every single one of the whole numbers, or the natural numbers, is included in the whole numbers. The only difference is that extra number 0. So that means the whole numbers are just a slightly larger set within which the natural numbers will fit. So what we can do is we can draw a, see if the W shows up there, there we go. We can draw a concentric circle surrounding that then fits around the natural numbers. So all those natural numbers fit inside the whole numbers, but because we have that extra number 0, it's a slightly larger number set. The next category of numbers is the integers. Intuition might tell us that we're going to use the letter I to represent the integers, but in fact we are going to use Z. And the reason is, if we look down the page a little bit, we can see that the irrationals also start with I, so that's where the I is going to come in. So the integers is the first place where we start to introduce negative numbers. Now we still are not using decimals or fractions when we're talking about integers, but we do introduce negatives. So again, we can reasonably demonstrate the pattern of the integers with a list. So let's say we start from -3, -2, -1, 0, and then 1, 2, 3, going up from there. So we can see there's no decimals, there's no fractions. We've just taken all of the whole numbers and then their opposites. Taken together, that's the set of integers. And so if we move to our Venn diagram, we're going to have another concentric circle here that is going to then represent the integers. Because again, all of the whole numbers 0, 1, 2, 3 fit within the set of the integers. We've just expanded the pie a little bit by including the negatives. If we go one more number set in the list, we've got the rational numbers. Again, intuition is going to lead us astray because the rational numbers are going to be represented by the letter Q instead of R. The reason being that it's the real numbers that are going to take that R abbreviation. And typically it's either kind of a fancy cursive R, you'll see it printed that way in a textbook. As you can see, I struggle with that cursive R. So my typical way, if I'm trying to talk about real numbers, is I'll make it a fancy R by making it a double bar R, just something to indicate that it is the set of real numbers. We've got to doll it up a little bit. So the rational numbers is where we no longer are going to describe or list off a set of numbers to show what type of numbers we're talking about, because it's just too complicated. So instead, we're going to go with a definition or a description of those numbers. So first of all, the rationals are any number that can be written as a fraction. So all fractions. So that's everything from 1/2, 2 2/3, 5/9. Negative fractions as well fall into this category. So all fractions. Or the other way that we could describe the rational numbers is in terms of decimals. And so it's any repeating or terminating decimal. And so terminating decimals are terminating, that means they end. So like 5.4, -3.27 would be examples of terminating decimals. And then repeating decimals are just any decimal that has like the bar over the number to indicate that it keeps on going forever. And so those types of decimals, whether they be terminating or repeating, are also those that could be written as fractions. So these are kind of interchangeable. It's not like it's fractions or these types of decimals. They all fall into the same category. And so the rational numbers are just going to be yet another concentric circle in our Venn diagram, because if we take a look at the natural or the whole or the integers, we can make those into fractions by just putting them over 1. So again, we're just expanding the universe of numbers as we go through these. But this last category, the irrationals, which we had indicated earlier, we were going to represent with the letter I. These are the opposite of the rationals. So now it's numbers that cannot be written as fractions. Or maybe a better way is to say that they are non-repeating, non-terminating decimals. And so these are numbers, one in particular that we might be familiar with is like the number pi when we're working with circles. 3.14159, it keeps on going forever and ever and ever. We'll sometimes round it off at 3.14, 159, but it really does go on forever. If you hit the pi button on your calculator, it'll fill the screen. If your screen had more space, it would include more numbers. Another example of an irrational number is like, let's say, the square root of 7. Square root of 9, for example, we know that works out evenly. It's 3. But the square root of 7 does not work out evenly. So that's another example of a type of number that is a decimal that does not repeat and does not end. And so in our Venn diagram, those now have to be a completely separate circle from the rational numbers. There's no overlap. A number cannot be both rational and irrational at the same time. And so that's why we're going to have a separate circle. We don't want to get thrown off by the idea that the size of the circle is smaller than what I've drawn for the rest. They're both infinite sets of numbers anyway. And then taken all together, we can say that all of these numbers are real. So rationals, irrationals together compose the real numbers. For the examples that we see here on the next page, you may want to try these on your own and then listen through to see what the categories are, what are the sets to which these numbers belong. But I'll go ahead and get started. So for the square root of 15, we just talked about those types of numbers. It's a square root that does not work out evenly. If it was square root of 16, that number would be 4. But square root of 15 is going to be a decimal that does not repeat and does not end, which means that number is irrational. Right? That's the only category that that's going to fall into. For the second example, 18/6, before trying to determine what categories that number falls into, we should reduce that fraction, and so we get 3. Now, when we think of the number 3, if we go back through the list of number sets that we just defined, we've got, it's a natural number. There we go. It's a natural number. It's a whole number. It is an integer. And because, as we saw it at the very beginning, it could also be written as a fraction, it is a, whoops, let me put a Q there. Let's try that again. So it is an integer. It is also a rational number. So we've got those 4 categories that it falls into. For the last example, negative 4.2, we may be tempted to say that that one is an integer, but recall that the integers, although that's where we introduce the negatives for the first time, do not include decimals or fractions. So negative 4.2, as tempting as it might be, it is not an integer. The only number set that it falls into is the rational numbers. So it is negative, but that's fine. Rational numbers can be negative, but it's a terminating decimal. So it's a rational number. And then all of these numbers fall into the category of being real. So we can use that fancy R to describe that, whether that's with the script or with the double bar. And really, since we're only operating with real numbers, if we left that off the list, it wouldn't be like we were missing out on any information. Same thing for the next set of examples. It may be worth it for you to spend some time thinking about these before continuing forward with the video, but I'll go ahead and get started. All rationals are real. We want to evaluate if that statement's true or false. Well, since all the numbers we're working with are real, that is indeed a true statement. All integers are whole numbers. Well, if we go back to our Venn diagram, the integers are a larger set than the whole numbers. Whole numbers are just 0, 1, 2, 3, 4, 5, whereas the integers include negatives. So this statement, as it's stated here, is false. However, if we reverse that and say that all whole numbers are integers, well, if we reverse that, now yes, all the whole numbers 0, 1, 2, 3, 4, 5 fit within the set of integers. So by reversing it, we turn it into a true statement. And then lastly, we kind of touched on this idea with the last example up above. Not all negative numbers are integers. So there's a counterexample provided right on the page for us. So we know that this statement is false. If it's an integer, it cannot have, it's not a decimal. No fractions, no decimals.